Hi, welcome to your Unit 2, Lesson 9 notes, which is all about logarithmic expressions. In this video, we're going to be working through all of examples 1 through 9. Your skills and learning objectives for this lesson are to apply the properties of logarithms to evaluate expressions with and without technology, logarithms to evaluate, use properties of exponents and logarithms to simplify and evaluate expressions, and understand each unit of the logarithmic scale is a multiplicative change of the base of 10. So 10 to the first, 10 to the 0, 10 to the first, 10 to the second, and so forth. All right, so we know that the logarithmic expression log base b to the n is equal to or represents the value that the base b must be exponentially raised to in order to obtain the value of n. So remember our transition back and forth that we've been working through. So log base b of n equals p if and only if b to the p is equal to n, where n and p are constants. B has to be a positive number and b cannot equal 1. Recall that when the base of a logarithmic expression is not specified, it is understood as the common log is of base 10. So some basic properties that you should all be aware of is if you had log base b to the 1, it doesn't matter what your base is, it's always going to be 0. If you have log base b, it's always going to be equal to 1. And then log base b to the y will be equal to whatever y is. And if you guys remember, there was a rule that said that you could put that y out in front. So it's y log base b, and we know that that's 1, because that's what we just said over there. So then you're just left with 1 times y, which would just be y. And then the reverse of that, if we had b as our base of our exponent, with the exponent being a log with the same base, those would cancel out and you'd just be left with x. Natural log of 1 is 0, natural log of e is 1, natural log of e of y is y, and then e to the natural log of x is just going to be equal to x. So natural logs and e cancel each other out. Okay, so for example 1, we want to give a reason for the following logarithmic expressions. So log base 2 of 8 is equal to 3 because, if I do the conversion, oops, I'm in highlighter mode, 2 to the third is equal to 8. Log base 3 to the square root of 3 is equal to 1/2 because 3 to the 1/2 is the same as the square root of 3. Log base 5 of 1 over 25 is equal to -2 because that would be 5 to the -2, which is equal to 1 over 5 squared, which is 1 over 25. And then log of 10 is the same as 10 to the 1, which is equal to 10. And then log base 6, 11 is equal to 11 because log base 6, 11 would be equal to, well, let me go back, right? So my base is going to be 6, so the base of my exponent becomes the base of my log to the 11 is equal to whatever this is left over, right? So that just is log base 6, 11. Okay, so converting back and forth. So here we are in exponential form, put it into logarithm. So 4 to the third would go to log base 4 of 64 is equal to 3. My base is 9, so that's the base of my log of 729 is equal to 3. Log base 2 of 1/32 is equal to -5. Log base 64 of 8 is equal to 1/2. Right, so we should be able to convert back and forth between log to exponential and exponential to log. Sometimes it's a lot easier to evaluate logs by converting them to exponentials because then it's easier to see. All right, example 3. Now it's asking us to write the logarithmic equation as an exponential equation, so doing the reverse. So my base of my log is 5. That becomes the base of my exponent. The 3 becomes the exponent is equal to 125. B, my base is 625, so that becomes my base of my power. The exponent is going to be 1/4, which is equal to 5. 1/2 to the -6, put this in parentheses, is equal to 64. And 2 to the -5 is equal to 1 over 32. So make sure you can do those transformations back and forth. Okay, common logs, base 10. So logarithms with a base 10 are called common logs. The subscript 10 is often dropped. So a logarithm statement with no specified base is understood to be base 10. On your calculator on the left-hand column where it just says log, that's assumed that it is base 10. So if we wanted to evaluate these without a calculator, because I could just use my calculator and type in log 100 and it will pop out my answer, but if we didn't have the calculator, we could do 10 to what power is equal to 100? Well, 10 squared, right? 10 squared is equal to 100. So log of 100 is going to be equal to 2. For B, 10 to what power is the square root of 10? Well, let's change that. So 10 to what power is 10 to the 1/2? Well, since I have like bases, I can set my exponents equal to each other. So x has to equal 1/2, so this whole thing would equal 1/2. 10 to what power is 1 over 1,000? Well, if I want to have a base 10 here, how can I convert 1 over 1,000 to base 10? Well, that's just the same as 10 to the -3 power. So since I have base 10, my x is going to be equal to -3. So log of 1/1000 is equal to -3. And then 10, so my base, so log base 10 of what is equal to log base 6 of 6. Well, on that right-hand side, so remember from our rules, right? 6 to what power? It's a little sidebar. 6 to what power is 6? So the whole thing is 1. So now we have log base 10 of x. So 10 to the first is equal to x. Converting it tells me that x has to equal 10. So this whole thing is equal to 10, which would make sense because that's just 1. So 10 to the first is 10. All right, moving on to example 5. Now we're going to evaluate using our calculator. Let me go ahead and pull up my calculator. Okay, so the first one we want to evaluate is log of 334.5. Just hit enter, and you all should be getting one. We're going to, let's go 4 decimal places. 1.5378 for your 5A answer. For 5B, we're doing the log of 0.43. That's me negative 0.3665 if I go to 4 decimal places. And then for the last one, log of -3, I'm going to end up getting a domain error, right? Because it's telling me I have non-real answers, which means it's not possible. So for 5C, it's not possible, right? Because I can't do 10 to a power and get -3. That's just not going to happen. If I made 10 to, let me bring this back up here. If I did 10 to a negative exponent, it's just going to keep getting me to like a smaller and smaller fraction, right? 10 to the -2 is, so there's no way that I'm going to be able to surpass below 0. So not possible. Okay, so D. Using your answer to example C, can you make a general statement about logarithmic functions? So logarithmic functions are not defined for negative values. Negative values, sorry for the really bad handwriting, of x. So our domain is going to be from 0 to infinity, but not including 0, because there's no way for me to get 0 either. Okay, example 6. Now we're going to get into evaluating each logarithmic expression, if possible, without using a calculator. So let's try to do these without a calculator. So log base 2 of 32 is equal to what number? So convert it to exponential. So 2 to the x is equal to 32. So maybe you are aware that 2 to the 5th is 32. But if you're not, just try to convert your 32 to a base of 2, right? So you could do prime factorization. 32 is 2 times 16, 2 times 8, 4 times 2, 2 times 2. So it's going to be equal to 2 to the 5th. So 32 can turn into a 2 to the 5th. And once I have my like bases, x can equal to 5. So log base 2 of 32 is equal to 5. For B, 49 to what power is equal to 7? Well, hopefully you notice that the square root of 49 is 7. The same thing as your square root is, so 49 to the 1/2 would get you to 7, because that's the same as doing the square root of 49, which is 7. So log base 49 of 7 is equal to 1/2. 1/64 to what power is equal to 4? All right, so maybe this one's not quite as obvious. So let's try to get two like bases. So again, let's do some prime factorization maybe. If I don't have a calculator, if I had a calculator, then I would just do trial and error to see what 4 to the what power would get me to 64. So 64 is 8 and 8, 4, 2, 4, 2. So we've got 1, 2, 3 4s. So that's going to be 1 over 4 to the 3rd is equal to 4 to the x. I'm getting really gross over here. I'm writing too big, I guess. So then I can make that into a negative, right? So that's the same as 1/4, or sorry, no. That's the same as 4 to the -3 to the x is equal to 4 to the 1. So now I have like bases. -3x is equal to 1 because of my equation, which means x is equal to -1/3. So log base 1/64 of 4 is equal to -1/3. I hope you followed that. I need to write smaller, I guess. For D, we're doing 5 to what power equals -25? Well, that's not possible, right? 5 squared is positive 25, but there's no way to get a -25, so not possible. But remember, we said we need to be in the positives. All right, number 7, use your calculator to evaluate. So if you remember on our calculator, let's bring that back up. On our calculator, if you have the TI-84, if you go to the math button and go to A, it'll give you your log base where you can type in your numbers. So log base 3 of 15, hit enter, gets you the 2.4650. Math A, log base 4 of 58 gets you the 2.9290. Math log base of 0.35 and 8.4. Oops, nope, come back. 8.4 gets you -2.0272. And then for the last one, log base 5/2. So just do 5 divided by 2 of 125. This is approximately 5.2694. If you don't have the TI-84 or anything higher, you do have to do change of base formula, which for log base 315, you could just do log of 15. Remember, your base goes in the basement, so log of 3. So then on my calculator, I would type in just log 15, because the 83s do have the log button, divided by log of 3, and we get that 2.46. So if I want to do the log 5/2, I would do log of 125 divided by log of 5/2, and then it gets you the 5.2694. Okay. All right, so now we're going to get into orders of magnitude and logarithmic models. So we're going to use order of magnitude to compare any like quantities. So using your calculator, and I'll just help you out. If I were to type in log of 3 times 10, that gets me 1.477. Log of 3 times 10 squared gets me 2.477. And then I get 3.477 all the way up to 10.477. So what do we notice? All your whole digit and your tens numbers, or your ones numbers, right, are going from 1, 2, 3, up to 10, with that 0.477 being consistent. So the pattern of the decimal is that it continues to be 0.477 is actually 1, 2. So how many orders of magnitude greater is 3 times 10 to the 10th, then 3 times 10 to the first, right? So if we're starting at the first, how many more magnitudes do we have to do? Well, it would actually be 9, right? So it would be 10 minus 1, which is 9. So it's 9 orders of magnitude greater. And the reason why we're talking about orders of magnitude is for the last couple problems here that have to deal with logarithms in application. So the first is the Richter scale that helps to measure earthquakes. So the intensity levels I of 2 earthquakes measured on a seismograph can be compared by the log of the intensity of the first earthquake divided by the log of the intensity of the second earthquake should be equal to the magnitude of the first minus the magnitude of the second, right? Which is given by the Richter scale. So how many times more severe was the 2001 earthquake in Gujarat, India, that had a magnitude of 7.9, than the 1999 earthquake in Athens, Greece, that had a magnitude of 5.9? So our magnitude 1 minus magnitude 2 should equal to the log of the intensity of the first divided by the intensity of the second. So 7.9 minus 5.9 should be equal to the log of the ratio of the intensities. So 2 is equal to the log of the ratios of the intensities. So now let's convert our logarithmic into exponential. The base of that log is 10. So 10 to the second, right? Take your base here, base there, the second goes there, is going to be equal to the ratio of your intensities. So my ratio of my intensities would be 100, right? So it's 100 times greater. So the earthquake in India is 100 times greater than the Greek earthquake. Oh goodness, earthquake, which has an order of magnitude is 2. Okay, so if the order of magnitude is 2, that means it's 100 times greater, right? If the order of magnitude was 3, then it would be 1,000 times greater, okay? All right, and the last one, example 9, is comparing pH and chemical acidity. So pH is modeled by the negative logarithm of your hydrogen ion concentrations. So it's a scale that measures how acidic or basic a substance ranks. The scale ranges from 0 to 14, where 7 represents neutral, and each whole pH value below 7 is 10 times more acidic than the next higher value. So there's your order of magnitudes, right? So every chunk of 7 is where your magnitudes change. So balsamic vinegar has a pH of 2.4, and a box of baking soda has a pH of 8.4. So we want to first figure out what the hydrogen ion concentrations are, so that H plus. So let's do vinegar first. So vinegar has a pH of 2.4 is equal to log of hydrogen plus your hydrogen ion concentrations. That's a common log, so 10 to the negative 2.4 is equal to hydrogen plus. I'm just going to divide out that negative, right? Move it over. So then it becomes my exponent. So 10 to the negative 2.4 is approximately 3.9 times 10 to the negative 3. And then moles per, is it liters, I think is the L. Yeah, maybe. Okay, and then your baking soda, do the same thing. 8.4 is equal to negative log hydrogen ion concentration. Move that negative over, convert to an exponential, base 10 to the negative 8.4 is equal to your hydrogen ion concentration. So that's about 3.98 times 10 to the negative 9 moles per liter. Okay, so there are your hydrogen ion concentration. So how many times greater is the hydrogen ion concentration of vinegar than the baking soda? So we're going to figure out how many magnitudes, right? So if we're doing vinegar compared to soda, vinegar is 10 to the negative 2.4. So baking soda is 10 to the negative 8.4. So bring up that negative exponent, means we're going to add it, which gets us 10 to the 6, which we could have gotten that with moving from negative 9 to negative 3 is 6 units, right? So vinegar is 6 orders of magnitude greater than 0. Or not 0, greater than soda. All right, here completes your notes.